Hi everyone. So a curious thing happened while I was making the video for assignment 53. My computer became unplugged, and as a result, I finished making the video, except the computer was off the whole time. So that's why you get two parts today. We had just, in that last video, found the derivative of y equals 5 to the x squared plus 3x. We said that derivative was itself times ln of the base times the derivative of stuff. Don't forget this derivative over here. Okay, so let's do one or two more of those, and then I'd like to find the derivatives of logs. So how about this one? Y equals 2 raised to the tangent of 3x. Pause the video, take the derivative of that, see what you get. It's a weird angle to the frame, isn't it? I must have spent 10 minutes, and this is the best I could get. I just think that it's a very interesting year we live in. All right, well, welcome back. And I've got y prime here as itself times ln of the base times the derivative of stuff. The derivative of tangent is secant squared, leave the inside alone, times the derivative of that inside, which is 3. Please don't turn this into 6 raised to the tangent 3x. We've got 3 times 2 tangent 3x. This is our exponential base. It doesn't play with that. Why? Because PEMDAS, exponents before multiplying. Right. Okay. So how about this one? Y equals 3 to the 2x secant 4x. Please take the derivative of that. Okay, so did you get y prime equals 3 to the 2x secant 4x times ln of the base times the derivative of stuff? That's a product rule. This times the derivative of that. The derivative of secant, oh, I hope you remember, secant tangent. Hey, but wait. We took the derivative of secant, but now we have to come back and take the derivative of the inside 4x. Are we done? No, that's only the first half of the product rule. This times the derivative of that. Now we need this times the derivative of that. And you're welcome to factor out a 2 secant 4x if you like, but it's not really going to get me anywhere, so I'm not going to bother. Okay, nice. Now, what was this derivatives of logs that I was going on about? So I can actually think about doing the derivatives of logs in a couple of different ways. One of the ways, in fact, kind of the way I prefer, is using something called the change of base formula. But when this came up in pre-cal last year, many of you looked at me like I had, horns growing out of my head or something, because the new calculators don't need the change of base formula. But, that doesn't mean it still can't be useful, and I do think the change of base formula would be very useful here. The change of base formula says if you've got log base b of m, you could rewrite this as ln of m over ln of b. And if log m over log b. I find, though, this one's really nifty to use, and this is the one I want to think about using. Not log or log base 7 of m over. Yeah, I mean, you could do log base 7 of m over log base 7 of b. But why? Why would you do that? So instead, I'm going to use this one. And so what I'm thinking is that I can rewrite this as ln of x over ln of a. Now, this is really, 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 really important. This is not a variable. This is a constant. That's a variable. That's a constant. The ln of some number. There's no variable here. The ln of a number is a number. So I really want you to think about rewriting this way. Why? Because I have a constant times ln. And how do we take the derivative of a constant times a function? We don't use product rule. The derivative of a constant times the function is the derivative of the function times the constant. So if this is how I understand y, then y prime is, remember, the derivative of the function times the constant. And so the derivative of log base a of x is going to be 1 over x ln of a. A is that number. So ln of a is ln of that log base. Okay? So this is one way to look at it. And so what does that look like? Well, if I have log base 7 of x, then I'm going to say, hey, that's ln of x over ln of 7. And if I want to find y prime, I want 1 over ln of 7 times the derivative of ln of x, which is 1 over x. And of course, if instead of x, we had 3x and 3x, I would say, hey, this is still 1 over ln of 7 times ln of 3x. And there's that constant, that 1 over 7. But now, the derivative of ln of 3x is going to be 1 over 3x times the derivative of that inside 3x, which is 3. Ding, ding. And so we end up with 1 over x ln of 7 again. Isn't that nifty? All right, so that's one way to go about deriving this. There's another way. Log base a of x equals y. You could do scorpion tail here, you know, and say that a to the y equals x, because sometimes it's fun to do scorpion tail. You could also exponentiate with a on both sides here. And so a to the power of log base a, these cancel as inverses, and so we have this. Okay, so now how do I take the derivative of this? No problem. The derivative of x is, I don't really want to have a y up there, so I better take the ln of both sides. And then I can bring this down. So I have ln of x equals y ln of a. Hey, if you divide both sides by ln of a, look where you are. But instead, I'm going to say the derivative here is 1 over x, and here we've got a constant times this. The derivative of this with respect to x is called dy dx times that constant. But I want dy dx alone, so I have to divide both sides by ln of a. And so dy dx equals 1 over x ln of a. See, I get to the same place, I just don't feel as good about that. But really, ultimately, my recommendation to you is you should memorize that when you have y equals log base a of stuff, that your derivative is going to be 1 over ln of a times stuff times the derivative of stuff with respect to x. That's inside the ln, that's not inside the ln. All right, so let's do some. How about this one? How about y equals log base 2 of 5x? That shouldn't be so horrible. Give it a try. Come back when you're done. Okay, so did you get y prime equals 1 over ln of the base times stuff times the derivative of stuff? And conveniently, the 5's really do cancel, and you end up with 1 over x ln of 2. Go. So let's step it up a notch. How about Sorry, really paranoid, wanting to make sure this thing gets not unplugged again. Okay, here's your problem. Log base 5 of square root of x. Come back when you're done with the derivative. Yeah, so before we get to the derivative, I actually want to take a little algebraic look at this for a moment. Isn't this the same as log base 5 of x to the 1/2 power? And because of that, couldn't I bring that down in front with that power property of logs? And so I could take the derivative of this and multiply it by that. So my y prime, oops, that's just y up there. My y prime would be that constant times the derivative of this, which is 1 over x ln of 5. All right, so how'd it go over here? Did you say that y prime would be 1 over ln of 5 times stuff times the derivative of stuff? Remember, this is x to the 1/2, so its derivative is 1/2 x to the minus 1/2. All right, well, let's see how this tidies up, okay? This is going to be 1 over ln of 5 times square root of x times this thing, 1 over 2, and this is x to the minus 1/2, which is that. And so now square root of x times square root of x is, that's right, x. 1 over 2 ln of 5 times x. Same. Either way, works nice. Okay, last log 1. Y equals log base 3 of 6x squared minus 4x. Please find y prime. All right, did you get 1 over ln of the base times stuff times the derivative of stuff, 12x minus 4? You're welcome to put that, a little tidier, 12x minus 4 over ln of 3 times 6x squared minus 4x. Yes, there's a tiny bit of canceling you could do. You could take a 2 out of everything. But yeah, I don't think I'd go any further than that. Good, so now we know logs. So a quick review of what we should know at this time. We should know when we have y equals b to the x, that y prime is going to be itself times ln of b. And if we have y equals b to the stuff, then y prime is going to be b to the stuff, ln of b times the derivative of stuff with respect to x. Chain rule. We also know that y equals e to the x, and y prime is e to the x. It's the same rule here, but remember, the ln of the base turns out to be 1. So we don't see that 1 the way we see if this were 2 to the x, ln of 2, we would see that connection. Okay. We also talked about y equals ln of x. Oh, no, we just did log. Sorry. Y equals log base b of x. And we said that derivative was going to be 1 over ln of b times x. Okay. Then, remember, y equals ln of x. That's the same as log base e of x. So y prime is 1 over x times ln of the base. Hey, that's 1. And that's why the derivative of ln of x is 1 over x. All right. So, what's left? Ha! We saved the best for last. Logarithmic differentiation. When I see y equals a function raised to the power of another function, that's when I use logarithmic differentiation. Okay? So when I see x to the x, a function raised to a function, that's when I want to do logarithmic differentiation. And we call it logarithmic differentiation and say it over and over and over and over because that's what we need to do first. We need to take the log of both sides. I take the ln of both sides and move this down. So we've got ln of y equals x, ln of x. Now I'm ready to take the derivative. Okay? So logarithmic differentiation, I take that log or ln of both sides first, and now I use derivatives. The derivative of ln is 1 over stuff times the derivative of stuff with respect to x. And over here, I see a product rule. This times the derivative of that, plus that times the derivative of this. Nice. Ooh, look, those cancel. So, almost done, but not quite. I still have to multiply both sides by y. And so I'm going to get dy dx equals y times 1 plus ln of x. Now, we really want everything in terms of x. So, remember, y shouldn't be here. What was y equal to? Y was equal to x to the x. Now I'm done. That wasn't so bad. Come on. You know it wasn't so bad. How about this one? How about y equals x to the tangent x? Okay? Remember, first thing I need to do, take the ln of both sides, because I have a function raised to a function. Don't confuse x to the 3. That's power rule. 3 to the x. That's an exponential, a constant raised to that variable. A variable raised to that constant. Power function, exponential function. Ooh, function raised to function. That's logarithmic differentiation. Okay? So I take the ln of both sides. That allows me to bring this down. I have ln of y equals tangent x, ln of x. Remember, that's multiplication. So I've done my logarithmic part. Now the differentiation part. Ln of y, 1 over y times dy dx equals, product rule. This times the derivative of that, plus that times the derivative of this. Not quite done yet. Remember, we need dy dx by itself, so I multiply both sides by y. And so now dy dx equals y tangent x over x plus secant squared x ln of x. But don't leave that there. Go back to the original. Y equals what? Y equals x to the tan x. Okay? I think it's your turn. So, what you got here? Y equals x to the cosine x. We'll do this one and one more, and we'll call it done for the day. Okay? Give it a go. Don't wait. Get to work. Pause that video. Give it a try. Hi, welcome back. So, did you remember to take the ln of both sides? That always has to happen first. Now what? Well, now we do the derivative. Sorry, 1 over y, dy dx equals product rule, cosine x times 1 over x plus ln of x, derivative of cosine minus sine x. So, dy dx equals y times cosine of x over x. God, no, you can't cancel those out. Minus sine x ln of x. And x to the cosine x. Okie doke. All right. So, last one. Oh, but it's a doozy. I saved the best for last. Here we go. Y equals cosine 2x raised to the power sine of 3x. So you can do this one without losing your sanity. You're well on your way. Maybe to losing your sanity. Okay, you're going to give it a try. Pause the video, give it a try. Just going to make me do it by myself. I hope this is welcome back. ln of y equals sine 3x ln of cosine 2x. Okay, careful. This is inside of that, but this and this are being multiplied together. And some students sort of lose that in all the symbols. Okay, so really I'm looking at this product rule. Over here, of course, 1 over y, dy, dx, and here, product rule, this times the derivative of that. Sine 3x, the derivative of ln of stuff is 1 over stuff, times the derivative of that cosine, leave that inside alone, times the derivative of the innermost 2. Phew! But not done, because that was just this times the derivative of that. Now we need this times the derivative of that. So we're going to have ln cosine 2x times the derivative of that, which is cosine 3x, times the derivative of the inside 3. Wow, that's a lot of stuff. And I still have to multiply both sides by y to get dy dx alone. Y dx equals y times negative 2 sine 2x sine 3x over cosine 2x plus 3 ln cosine 2x times cosine 3x. Woof. But wait. We have to replace this with cosine 2x raised to the power of sine 3x. Wow. Like I said, if you make it through this without making any mistakes, you're fabulous. God, I hope I'm fabulous. There's so many places to get lost. Let's just check. This times the derivative of that, and over stuff, times the derivative of cosine, beat that, times the derivative of that, nice, plus this, yes, times the derivative of this, yes, times the derivative of that, yes. Wow, yeah, there it is. You could turn this into tangent 2x. Yeah. I mean, that's what it's going to be on the multiple choice portion. 2x. Oh, 2x. All right. So there you go. Logarithmic differentiation. When you use logarithmic differentiation, when you have a function raised to a function. Please do not use logarithmic differentiation when you have this. You should know this one. This is y prime equals itself times ln of the base. Okay? All right. So go and practice a bazillion of these so you can get really comfortable with them. Promise, it's really important. I also recommend you go back to that bell work problem we did in part 1, where we were talking about f inverse prime. You really need to be able to do f inverse prime of x. Yeah, watch that again. Okay, have a wonderful day, everyone.